All right, so thank you everyone for coming to our talk, PIBuster, exploiting a common misconfiguration in CCS EV chargers. My name is Marcell Szakály, and this is work that I've done with my colleagues at the System Security Lab at the University of Oxford, as well as with some funding and support from our partners at ArmaSwiss. So just as a quick intro, though I think we've seen this now a few times, basically you've got AC charging and DC charging. And in AC charging, you just put electricity into the car and it knows how to charge itself. In DC charging, you have a sophisticated communication link going through the charging cable between the charger, which is external to the car, and then the battery, which is actually located inside. So if you've seen these plugs, these are the ones that we'll be talking about, as these are all the DC charging plugs here in Europe, as well as in Europe, the US, and some other parts of the world. And yeah, as Jacob also mentioned previously, they all use the same underlying communication standard called ISO 15118. So what does ISO 15118 actually do, just in a bit of detail? So as you plug in the charging cable, it does something called basic signaling. This is just a hot plug presence detection for the wire. Then you have power line communication, which is what establishes a sophisticated Ethernet link over the charging cable. And then finally, on top of this, you've got the vehicle-to-grid protocol, which does essentially a sophisticated IP stack and a lot of communications related to safety, timing, billing, as well as any other features that get added to the standard. And once you finally set all of this up, power can actually start flowing into the vehicle. So for the purposes of this talk, we'll be focusing entirely on the power line portion of this protocol stack. So in one of our previous studies, which is actually going to get presented at main USENIX on Friday, we conducted a measurement study. And one of the things we found is that all of the chargers in the wild use the QCA 7000 series chips to do their home plug signaling. So these are modem chips that need to be located in both the car and the charger to facilitate the communication going through the charging cable. And so this little chip you can see in yellow circled on one of our developer boards. That exact thing is in all cars and chargers, basically, that support these protocols. Also, as part of our measurement study, what we saw is that a lot of them use outdated firmware. So we're looking at firmware from 2013 or 2015 quite often. Over half the chargers have firmware that is more than 10 years old running on these communication chips. For example, we also saw that even though broken wire, which was an attack discovered by one of my colleagues, exists in the physical layer of HomePlug, and it is something that we believe could potentially be fixed by firmware. In the 2 years since the attack was disclosed, no single charger has firmware that is actually newer. So there's no way it could have been fixed so far. So with these, we kind of got motivated to research deeper into these modems to understand what sort of security risks they hide, because clearly they are not an essential part of the security landscape of the EV charging ecosystem, as from the manufacturer's point of view. Unfortunately, information on them is extremely limited. You can't download the firmware, you can't access data sheets. Everything needs NDAs with Qualcomm. So we got our information from two open source places. First of all, the OpenPLC utils package, which is essentially for home users who use Powerline at home, because turns out it's the exact same technology that you use in EV charging that you would, for example, use if you bought these Ethernet over Powerline adapters. And for those, they have released a set of configuration tools that you can use to set up your home network, to override their configuration and do all sorts of important things. And the other project we used was HomePlug Pawn, which was made by a researcher who kind of looked into these chips and reverse engineered some of their features. So the main finding from this was that they contain something called the parameter information block. It is a large binary configuration file. You can see a snippet of it on the screen. It contains important settings like a MAC address or a manufacturer device string, for example. And it just keeps going for about 10 kilobytes more of binary settings. And this is something that you can easily change if you own one of these modems and you connect to it. OpenPLC utils provides the command to do this, but you just send a special management message over Ethernet to the chip, and it will update the configuration file. What we found interesting, however, as we were playing around with this, we noticed that there is a mandatory MAC address argument. So we wondered what happens if we type in the MAC address belonging not to the chip on our side of the communication link, but on the other side. And this is how we discovered the PIBuster attack, which essentially means that, yes, you can send this configuration override message from your host system to your power line modem, from the power line modem over the power lines to the remote modem, which will actually execute it. So this means that just via the charging cable, an EV could update the configuration inside of a charger, and the charger could update the configuration inside of an EV. Now, how bad can this really be if it contains just a MAC address or a manufacturer string? Well, we found specific bits in this configuration which you can use to permanently disable the modems, essentially bricking all communications and making sure that that charger can never charge anything or that car cannot be charged in the future. So in our limited lab testing, we quickly saw that this only works on some of the devices we have, even though the firmware was always stock. There is, as far as we can tell, no way for vendors to make their own firmware. So what could the difference be? Well, we assume that the only difference is the configuration file itself. So there must be some sort of security setting inside of this PIB that can disable the attack. Unfortunately, this meant that we were looking for one bit in approximately 10 kilobytes without any documentation for most of it. To conduct our investigation, we first obtained a PIB from both a vulnerable and a secure device, one of our portable EV chargers, as well as a development board. And we found many differences, including the file size. We then put them onto the same modem. We devised a simple test procedure where we get two power line modems, connect them to each other via the power lines, but also connect them to kind of a host system via Ethernet. And then we can put something onto the victim and then try attacking it via the attacker side through the power lines to see if it actually works. And with this, we saw that the two different PIBs behave differently on the different modems. So the next thing we did was we kind of started merging the PIBs, first half from the secure one, second half from the vulnerable one, and then did binary search on the cutoff point based on whether the attack still worked or not. And we used this to narrow it down to the security bit at 1F8C deep inside the file. But what we also found is that, so we found that if it's 0, the reading and writing is allowed, and this is the default when you purchase a new development board. And if it's set to 1, then it is blocked. So we set out to do some data collection. We created an EV emulator that you can see here. If you can plug it into chargers. Inside it contains the same power line modem as well as a Raspberry Pi. We went up to real-world chargers and attempted to download the PIB from them. If it was blocked, we assume it's secure because there is no way they're going to let us write if they don't even let us read. But we can't ethically test writing in the wild, of course. But if reading is possible, then we used our previous lab setting or lab setup to test the real configurations we've downloaded on real hardware to see if writing is possible. And what we found is that out of the 69 chargers we tested in California, 41 allowed us to download the PIBs, and out of these 41 were not write protected. So this is a vulnerability that is quite prevalent in the wild. Quickly, I would also like to mention host booting. So there is an option in the standard where the PLC chip can run without having any flash chip. This means that it doesn't have its own firmware and it doesn't have a persistent place to store its configuration. Instead, it downloads it every time from the host system as it boots up. This is used by some devices. If you buy PLC as a module that you can see here, it's likely going to have an integrated flash chip to be a nice self-contained system. If the PLC chip is kind of an integral part of the circuit board design, it's more likely to be host booted. Host-booted systems, because they don't have any persistent storage, you are somewhat vulnerable or somewhat immune from this attack because you cannot put a configuration on there forever. However, until the next reboot, it is still vulnerable. So, as responsible researchers, we disclosed to Qualcomm in February. They acknowledged that they are treating this as a vulnerability, though they also did mention that essentially the setting as we found is provided, so manufacturers should have turned it on. And in the next firmware release, they will hard code to block all remote PIB read and writes. So finally, as our discussion, first of all, everyone out there running any sort of charging company should make sure to set their PIB security bit at the location we mentioned. Next up is to more generally update the firmware on the device. And finally, we would like there to be more research from the entire security community into these power line chips because they are essential. They are a hardware part of the standard, so they can't realistically be replaced via a protocol version upgrade. So thank you, and if you have any questions.